Hello there, Mr. Sutton bringing you the BC Calculus Quiz 2 review solutions for Chapter 6, this topic being motion and accumulation with rate in, rate out. For this problem, we have the acceleration of a particle along the x-axis given as a of t equals 6t minus 2, and they're telling us the velocity is 25 when time is 3 and position is 10 when time is 1. Based off all this, they want the position function. So unfortunately, we can't go all the way from acceleration down to position in one step. We first need to find the velocity function based off of this information, and then we can use that to find the position function. So to go from acceleration to velocity, if you just want the function and not an actual value, you need to use diff-EQ math. So I'm going to take the antiderivative of both sides here. I'm going to get a plus c constant of integration, and then I'm going to use this initial position, time 3, velocity 25, to figure out the c value. So first step, antiderivative of a, that's going to be v of t. And then over here, 6t, that bumps up to a 2 for the exponent. Dividing by that, we have 3t squared minus 2t plus c. So they told us when time is 3, velocity is 25. So I can plug in 25 for v of t, and then I'll plug in 3 for all the t values on the right side of the equation. So on the right side of the equation, we have, let's see, this is 27 minus 6 is 21 plus c. If we subtract 21 from both sides, we get a c value of 4. So then I can rewrite my velocity function as 3t squared minus 2t plus 4. Now we're going to try to turn this velocity function into a position function. So I'll start just like I did up here by taking the antiderivative of both sides. On the left side, we've got x of t. And on the right side, this is going to be, let's see, that bumps up to a 3. Dividing by that, we have t cubed minus, this is going to be t squared plus 4t plus c. And now we'll use this initial position of 10 when time is 1 to figure out the c value. So I can plug 10 in for x of t. And then all the t values on the right side are going to be 1s. So we have t cubed, so 1 cubed minus 1 squared, which is just going to be 0, plus 4 times 1. So when the dust settles, we just have 4 plus c on the right side. Subtracting 4, I get a c value of 6. And plugging that back in, I now have t cubed minus t squared rather, plus 4t plus 6, which gives me answer choice C. For the next several problem parts, we're going to be using this velocity function for some particle moving along the x-axis. And because these are all calculator questions, I'm going to go ahead and actually plug this into my calculator right away. So here I am in my y equals. I've plugged this into y1, and now let me tackle the first problem. So we've got, let's see, they want to know the displacement of the particle from time 0 to time 3. So displacement, this is the total change in position from one time to another. So to figure this out, I need to take the rate of change of position, which is velocity, and I need to integrate that from whatever the interval is, so 0 to 3 in this case. Because velocity, that's your change in position. The total change is the integral of that. So I'm going to do integral from 0 to 3 of v of t dt, and now I just have to put that on my calculator. So on the calculator, I'm going to do math 9, integral, so 0 to 3, and I'll do alpha trace and y1. That again is where I stored my velocity function. I'll dx this thing, and that comes out to approximately negative 2.197. For part B, they want to know the position of the particle described here at time 5. So to find the position, I need to know the initial position, and they said at time 0 we were at the position 1. And then to that position, I need to add the displacement from time 0 to time 5. So I'm going to do 1 plus the integral from 0 to 5 of velocity. Because again, I'm just adding the total change in position right here. So let me do that on the calculator. So here's what that looks like on my calculator. Again, I stored velocity in y1, so I don't have to keep rewriting it for every problem. And press enter. And this is going to come out to about 0.3097, so I'll round it off to 0.310 for 3 decimals. For part C, they want to find the total distance traveled by our particle from time 0 to time 3. So total distance is pretty similar to displacement, except displacement counts negative steps as negatives, whereas total distance, you want to count every step taken in any direction as a positive quantity. To make this happen, we're going to still integrate velocity over the interval from 0 to 3, but we're going to instead integrate the absolute value of velocity rather than the original velocity. So this makes sure that all of those negative steps in any direction turn into positives. So going back to the calculator now, I need an integral, so math 9, still going 0 to 3 now, like we did earlier with velocity, and I need absolute value, so I'm going to do second, or rather alpha, and then window, and that gives up a menu here where I can pick absolute value. Let me do alpha trace now and put y1 in there, and then dx. So our total then is going to be roughly 4.334. For part D, they want the average velocity of our particle from time 0 to 3. Now, you found average velocity in earlier chapters by taking the displacement formula or the position formula, s of t, and finding the average rate of change of that function on whatever interval you were dealing with. But here we're starting with the function, the velocity function that we want to find an average for. So in a situation like this where you've already got the function you're trying to average, we use the average value setup with an integral. So I'm going to do 1 over b minus a, which in this case is 3 minus 0, 1 over the interval length times the integral from 0 to 3 of whatever we're trying to average, velocity in this case, so v of t dt. And now I'll have to plug this in the calculator. So here's my setup on the calculator. I've got my 1/3 on the outside, 0 to 3 integral. y1 again is where I stored velocity. Pressing enter, that comes out to negative 0.732. For part E, we want to know if our particle is moving toward or away from the origin at time 5. Well, in order to figure this out, we need to know which side of the origin we're on, the left or the right, and also which direction we're moving, to the left or to the right. So we need to know our position and our velocity. Fortunately, we already found the position of our particle at time 5 in an earlier problem. Just to review what that was, x of 5 was about 0.310, which is to say, a positive quantity. So that means we are on the right side of the origin, on the right side of the y-axis. So all we have to figure out now is, are we moving to the left or to the right? For that, I need velocity at time 5, which I can quickly find on the calculator. Since I stored my velocity function as y1, I can just do alpha trace y1 and then open a parentheses and put 5 in, just like plugging a number into a function. And that comes out to about 0.398, which is also positive. So we have the same sign for x of 5 and v of 5. Since we are on the right side of the origin and moving to the right, since these agree essentially, that means I'm moving away from the origin. Now, if these two quantities had opposite signs, so for example, we were on the right side but moving left, or on the left side but moving right, then we would be moving toward the origin. So it's all about whether x and v share the sign or have opposite signs. For this problem, from time 0 to 31, the rate of change of the number of mosquitoes on Tropical Island, it's a creative name, at time t days is modeled by this r of t function. And this is in this mosquitoes per day. There's 1,000 mosquitoes to start at time 0. For part A, we want to show that the number of mosquitoes is increasing at time 6. So before I do anything else, I'm going to go ahead and store this r of t function on my calculator under y1, just so I don't have to keep rewriting it on the calculator. So here I am in y1. This is what my function looks like with x's instead of t's, because that's my input variable in the calculator. And now to show that the number of mosquitoes is increasing at time 6, I need to get the rate of change of mosquitoes, which is actually this r of t function they gave us, and simply plug in 6 to see if that comes out positive or negative. So let me calculate r of 6 on the calculator. So going back to my calculator, let me quit out of my y equals. And now to plug into that function, I'm just going to do alpha trace y1, open a parentheses and put 6 in there. This is just doing r of 6 on the calculator. This comes out to 4.438 and some change. Now significantly, this is a positive number. Since the rate of change of mosquitoes is positive, that means the number of mosquitoes is increasing at time 6. For this next problem part, they want to know at time 6 if the number of mosquitoes is increasing at an increasing rate or increasing at a decreasing rate. And before you think, well, they gave me something here because they're implying it's increasing, well, they already said it was increasing in part A. They just wanted you to prove it to them. So which of these is it going to be? To figure out the rate at which the rate of mosquitoes is changing, we need the derivative of this r of t function. So we need r prime of 6. And since we've already got the r function entered under y1 on our calculator, let me just clear that out. I'm just going to do derivative of y1 at 6. So let's do math 8. I'll do dx there, and I'll do alpha trace y1. And then we'll just plug in 6 to see what this comes out to. It comes out to negative 1.913. Now, the important piece of information here is that this is negative. Therefore, the rate of mosquito, or the number of mosquitoes, is increasing at a decreasing rate. This is essentially concave down on the increasing end. So increasing at a decreasing rate. For part C, according to the model, how many mosquitoes will be on the island at time 31? Round to the nearest whole number. Okay, so we already have a function that gives us the total rate of change in the number of mosquitoes. We don't have to worry about mosquitoes being born and dying. This function takes all of that into account. All we have to do is take the initial number of mosquitoes and add the total change in mosquitoes from time 0 to time 31. So I'm going to define a function here, m of t, that's the number of mosquitoes. I'm going to say m of 31 equals the 1,000 that we started with, plus the integral from 0 to 31 of r of t dt. And now I need the calculator. So here we are, 1,000 plus math 9 integral from 0 to 31, alpha trace y1 dx, all that jazz. Let's see how many of these little buggers we've got. The calculator doesn't want to fathom this horrible situation. 964 mosquitoes. They wanted us round to a whole number. We don't want a part of a mosquito. We don't even really want a whole mosquito. But we'll take what we were given here. For part D, to the nearest whole number, we want the maximum number of mosquitoes on time 0 to 31 and show analysis that leads to our conclusion. So one such analysis you might do is the candidates test, since we're looking for an absolute extremum on a closed interval here. We're going to plug in the endpoints to figure out how many mosquitoes we have at the beginning and the ending of the time in the problem, and we'll also plug in any critical values we find along the way. To get those critical values, though, we have to set the rate of change of mosquitoes, r of t, equal to 0 and find intersections on our calculator. So let's go ahead and do that now. So again, just to recap, I have r of t stored as y1 in my grapher, and I'm going to go to Window now and graph that from 0 to 31, because all of these values are candidates for being the min or the max. So let me do zoom 0 now, zoom fit, and let's see what this looks like from 0 to 31. So we've got one critical value here, and I got another critical value over here. So this is two places we've got critical values. Now, since we're looking for the maximum number of mosquitoes, we only need to consider local maxes, not local mins. This spot over here, for example, where r changes from negative to positive, that's a local min. There's no way a number that's smaller than the numbers around it is going to end up being the biggest number for the function. So the way I'm going to do this, I'm going to find this intersection, this first intersection. Let me do second trace, zeros, and then let me move my little spider over here. Maybe the spider could catch some mosquitoes. So we enter to the left, press enter again to the right, enter one more time, and that gives us a value of about 7.854 if we round off. I am immediately going to quit out of here and store that as a value. I'm going to store that as alpha A. I guess I could store it as alpha M, but I'll do alpha A, just so I can pull that value back when I need it. And the way I'm going to express this in my work, in my analysis, is that r of t changes from positive to negative, which is the conditions for a local max, at t equals a equals this number only. So I'm saying, I've got this critical value at 7.8 and change. That's a local max. And that's the only local max, even though there might be other critical values. That's the only local max. So that's the only one I'm going to consider for my candidates test. Notice that I've also stored it on my paper as A, so I don't have to rewrite this ridiculousness over and over again. All right, so now it's on to the candidates test. Let's start with, let's see, now I defined my number of mosquitoes function as M in part C. So M of 0, that's just the starting mosquitoes, that's 1,000. Now we're going to do M of A, the number of mosquitoes at time A. That's going to be the 1,000 we started with, plus the integral from 0 to A of R of t dt. I'll need the calculator to actually figure this out now. So here's what this one looks like on the calculator. 1,000 plus integral from 0 to A. Y1, again, is where I stored my R function, dx. And how many mosquitoes is this to the nearest whole number? Drum roll, please. Buzz, buzz, buzz. We've got 1,039 mosquitoes, which is more than we started with. So far, this is the number to beat. All right, now let's do M of 31. Well, hold on a sec. We already calculated that on the last problem part, right? M of 31 we already found was 964. I was about to do 1,000 plus integral from 0 to 31, but we already found it in part C, so why bother? Our max then, they just wanted to know the max number. They didn't care about when it happened. Our max, which happens at time A, is 1,039 mosquitoes. On this problem, a water tank at Camp Newton, where they sing about derivatives and integrals, holds 1,200 gallons of water at time 0, and during the interval 0 to 18 hours, water is pumped into the tank using this W of t rate, and during the same interval, water is removed from the tank at a rate given by R of t, and all this is in gallons per hour. So there's your setup. We have a rate in and a rate out, and I mean, we know where this is going, so I'm just going to enter these in the calculator right away. So let me show you what I've entered on my calculator. W of t, I've put in my y1 function, so 95 radical x I wrote it, and to get the sine squared action here, I need to open a parentheses with sine of x over 6 inside of it, close that whole big parentheses, and then I'll put my square outside. I did the same thing down here in y2 for r of t, which also had a sine squared in it. So we've got r of t and w of t entered in the calculator. And now, for the actual problem here, part A anyway, is the amount of water in the tank increasing at time 15, why or why not? So I know where this is going in terms of these types of problems. They always have a rate in, a rate out, and they always ask you to combine them in some way to find the overall rate of change for the function. So I'm going to make a function to represent the amount of water in the tank. I'm going to call it G of t, G for gallons, so that's gallons in the tank. And I can define another function, G prime of t, which tells us the rate at which the water is changing. That's just going to simply be the rate in minus the rate out. So W of t minus R of t. And I'm going to need to use this, so I'm going to go back to my calculator, and in my Y3 now, down below here, I'm going to just do Y1 minus Y2, so alpha trace Y1 minus alpha trace Y2, and now my Y3 is this G prime total change in water kind of function. All right, so what do I actually need to do to find the whether my water is increasing at time 15? I just need to plug 15 into G prime and see if it comes out positive or negative. So going back to my calculator once more, I quit out of my Y equals, and I'm going to do alpha trace Y3 to use my G prime function. I'll just open my parentheses and put a 15 in there, close the parentheses, and this comes out to negative 121.090. And this, of course, is in gallons per hour if we needed the units. I don't think we did, though. But significantly, this number is negative. That means that the water is not increasing at time 15. In fact, it is decreasing. For part B, they want to the nearest whole number the number of gallons of water in the tank at time 18. So after this period at Camp Newton in which the problem takes place. So this is where I'm really glad that I actually defined a function to represent the amount of water and also the rate of change of the amount of water, because I can just use that now on this problem. So I'm going to say that G of 18, my gallons of water at time 18, equals my water that I started with, this 1,200 gallons of water, plus the integral from 0 to 18 of g prime of t dt. So I'm just taking the rate at which the water is changing, and this integral gives me the total change in water after time 0. So let me use the calculator for this. So I've got 1,200 plus integral, math 9, 0 to 18, y3 again was where I stored my g prime, and this comes out to approximately, they want the nearest whole number, the nearest gallon. It's taken a while, 1,310 gallons of water. For part C, they want to know at what time between 0 and 18 the amount of water is at an absolute minimum. All right, so to figure this out, we're going to use the candidates test. I'm going to plug 0 and 18 into my g of t function, and also any critical values that I find between the interval 0 to 18. To get those critical values, I need to take the derivative of g prime, and set that equal to 0, and I'll solve that now on the calculator. So here in my y equals, g prime of t, remember, was y3. Now I don't want to graph the other ones, so I deselected those so that I'm not graphing 3 things at once. And I'm going to do window, and I'm going to set my window to be from 0 to 18. I don't care about anything else. Zoom 0, zoom fit. Let's see what this looks like now. So we're looking for places where this crosses the x-axis. And we see here that there's, one crossing there. Are we going to get another one? Yes, we are. How about a third one? Nope, it just missed the cutoff. Maybe it crosses, maybe it doesn't. But we don't really care. We're just going to go with what we've got for these 2 critical values. Now, I say 2 critical values, but we actually don't even need both of these because we're looking for, they said, an absolute min. That means that the only critical values that really matter are local mins. Local maxes, like the one over here where g prime is changing from positive to negative, local maxes don't need to be tested because if you're a local max, you're the highest value in your immediate area, which means there's no way you're the lowest value for the whole graph. So we're just going to find the intersection over on this first critical value. So second trace, zeros. And let me move my spider to be a little bit to the left. Press enter, move a little to the right, press enter, doing my zero dance here. Enter one more time gives us a critical value of 6.495. And I am immediately going to quit out of my graph and store that value. And I'm going to store that as just alpha A. Now I can go back and use that value anytime I need to, just in case. Now, here is what I just graphed out. I'm going to write down for my work that g prime of t equals 0 and that g prime of t changes from negative to positive at t equals a equals 6.4948 only. So I've done a few things with this statement. First off, I'm storing this crazy value as a in my work. So now whenever I want this number, I can just write a in my actual work, and they have to accept that that's what a means. The other thing I've done here, I said g prime changes negative to positive. That's saying that, hey, I've got a local min here. And I put the word only over here. I'm saying this is the only local min, so this is the only critical value I'm obligated to test out with my candidates test. All right, so we don't even have to test that other one. Let's just test this one critical value, 0 and 18. Testing 0 is pretty easy. That's just the amount of water we started with. That was 1,200. So g of 0 is just 1,200. G of a, on the other hand, is going to take a little bit of calculator work. That's going to be the 1,200 I started with plus the integral from 0 to a of g prime of t dt. Let me go to the calculator for that. So we've got 1,200 plus math 9 for integral, 0 to a. I stored this as a, so I'll just do alpha a. I also could have just arrowed up and stolen that output from before, but I like it this way better. It looks a little cleaner. And now, where did I store my g prime in the calculator? Oh yeah, that was in y3. So let me do alpha trace y3. And then dx. So a lot of things I had to put together there, but the amount of water at time A is 525. And let's see, a little bit of change here, so there's the rest of the decimals. Let me just make sure that's correct. Yep, 242. Great. And that's in gallons. Okay, so one more here. we needed G of 18. But as luck would have it, we actually already found that on another problem part. That is actually 1,310. Now we were looking for the absolute minimum. That was 525.242. But we don't actually care about the minimum as it would happen here, because they wanted at what time that minimum happens. So for the actual answer, you need to go back and say, okay, we reach an absolute minimum at time A hours. For part D, final boss battle as it were, they're telling us for time greater than 18, because this stuff only works for 0 to 18. For time greater than 18, no water is pumped into the tank, but water continues to be removed at the rate R of t until the tank is empty. Let K be the time when the tank is empty. Right, but don't solve an equation with an integral expression to find the value of K. All right, so let's talk about what's happening with this water after 18. After 18, we're adding up just this R function here, where water is being pumped out. So we can write an expression for the amount of water that is pumped out after time 18. That's going to be the integral of R of t from 18 to whenever K is. So there we go. That's the expression for all the water that we lose after time 18. Now, how much water do we want to lose? Well, we want to keep pumping until the tank is empty. So how much water was actually in there at time 18? You might remember from one of the problems earlier on this problem set that was 1,310 gallons of water at time 18. So if we set this integral equal to this number, this now gives us an equation that we can use to solve for K.